All right, so I'm going to write down three matrices. First is going to be a 2 by 3, and then I'm going to write down another 2 by 3 matrix and call it B. 2, 2, and 0 for the second row, and then a matrix C, which is going to be a 2 by 2. And there we have it. Okay, so let's practice some arithmetic. Let's add the matrices A and B. So the rule I wrote down on the previous page, we're going to come back to that in a moment. First, I want to just show you probably what most people would think of as a simpler way to perform this operation. Let's just write down a copy of A and I write down a copy of B and on our next step. So we're just going to replace the letter A with what that matrix actually is, and same with B. We've got -4, 3, and 5, and 2, 2, 0. So here's our matrix A, and we're adding it to the matrix B. Well, both of the matrices A and B are 2 by 3. So the sum is also going to be 2 by 3. So we can just agree on that right off the bat. Now, if I want to work out these three entries in the first row and then these three entries in the second row, just take the corresponding matrices from entries from A and add the corresponding entry from B, and that will give you any of the particular entries in the sum. So in other words, if I went 2 plus -4, which is -2, that's going to give me the entry in the first row, first column. Then if I go 1 plus 3, it's going to give me 4. That's going to give me the second entry in the first row. And then similarly, 0 plus 5 will give us 5 right there. And then for the second row, I go -1 plus 2, which is +1, 0 plus 2, which is 2, and then 2 plus 0, which is 2 as well. So that's probably the most straightforward way to compute the sum of two matrices that have the same size. Remember, if they don't have the same size, you can't add them together. Because if I were just to go back to the previous page where we wrote down the definition of addition, it worked as follows. So if A and B are both m by n, so in other words, they have the same dimensions, then the sum and the difference are going to be the m by n matrices defined by this rule and this rule, right? So that's how we know right away. But if A and B weren't the same dimensions, then this would not be satisfied and the rest of the definition is not valid. But let's take a look at, just to say we did, let's look at one of these entries and look at how we would compute this one formally using the rule. Well, here's how you would do it, right? That is the entry from A plus B, which is in the first row in the third column. So you'd take, notation-wise, that's A plus B entry in the first row, third column. But now that's when this rule kicks in, right? We can use this rule to evaluate. If I want the 1, 3 entry from A plus B, just take the 1, 3 entry from A and the 1, 3 entry from B and add them together. That's what the rule says. So we can follow this very carefully, and we would start by going, take the 1, 3 entry from A and add it to the 1, 3 entry from B, and then look them up. So in A, the 1, 3 entry, that's 0. But in the matrix B, the 1, 3 entry, well, first row, third column, it's a 5. You'd have 0 plus 5, which of course is 5, and that's what we had. We were expecting to get 5, because that's how we got it. We went 0 plus 5 is 5. So really you are using this formal rule even if you don't write it down for every single entry. But if you did write it down, this is what it would look like. So that's just for that one entry. Let's do a subtraction. So we'll go A minus B. And we'll start by doing the same thing. Just write a copy of A. And then we'll subtract a copy of B. All right, well, A minus B is also going to be a 2 by 3 since both of these two operands were 2 by 3. So the result will be 2 by 3 matrix. So if I want the entry in the first row, first column, I'm going to go 2 minus -4. So that's like 2 plus 4, which is 6. If I go 1 minus 3, I get -2. And if I go 0 minus 5, I'll get -5. So that's how I can fill in the first row. Second row, I'll go -1 minus 2. That's going to be -3. 0 minus 2 will be negative 2, and then lastly 2 minus 0 will be positive 2. And again, just to say we did, let's do one of these calculations formally as well. So let's say I wanted to compute the entry of a minus b, which occupies the first row in the first column. Well, that notation-wise, that would be a minus b in the first row, first column. So just flip back to the definition. You've got a minus b, you want the entry in the first row, first column. Just take the entry from a in the first row, first column, and subtract the entry from b in the first row, first column. So we're just using this definition here. And what that would look like is the following. We just go a 1, 1 minus b 1, 1. So what's the entry from a in the 1, 1 position? Well, that's a 2. The entry in b in the 1, 1 position, that's a negative 4, but we're subtracting it. So we're going to have minus negative 4, which is going to be 2 plus 4, which is 6. And again, that's what we had, right? If I go 2 minus negative 4 is equal to 6, 1 minus 3 is equal to negative 2. Really, I'm doing this procedure entry by entry, but I don't have to write it down every time. But again, I did one formal calculation for each of these operations, but typically you may find that you don't want to write these down, and that's totally fine. Maybe you might need to do it in theoretical circumstances, but if you're just directly adding or subtracting matrices, you don't have to write this down every time. One last addition. What about a plus c? And it's not defined. And the reason for that is the dimensions are the same, right? A is a 2 by 3 matrix, and C is a 2 by 2 matrix. And somebody might argue, even convincingly maybe, they might say, yeah, okay, well, if there's only these 4 entries, just take those 4 numbers and add them to these 4 numbers, and then leave those 2 alone. And you could do that, but that would not be what matrix addition is. Matrix addition is not defined in this case because, let me just one last time go back over here. In order for the sum and the difference to be defined, both the matrices A and B that you start with have to be the same size. That's the significance of this first line. So it's crucial that they have the same dimensions. So in this case, A plus C is undefined. Same with A minus C. Okay, so that's a couple of straightforward examples. Next, we'll talk about another operation called multiplication. Now, we've already talked about multiplication in the context of scalar multiplication. That told us how to take a matrix and multiply it by a scalar. But that's not what we're going to do now. Here, we're going to actually multiply a matrix by another matrix. And it turns out, you might expect that it's going to be straightforward like the previous operations, and it is straightforward in some sense, but it takes a bit of getting used to, and the definition is not as natural as you might expect. So it's actually going to apply in a very specific circumstance, which I'm going to outline now. So let's say we have 2 matrices, A and B. So I'm going to start by writing A in this form. I introduced this at the very beginning of the section as a possible way that you could write down a matrix. And I'm going to take advantage of that right now. So remember, if I write this, what I'm saying is let A, capital A, be an m by n matrix, and I'm going to use this notation to represent the entry that's in the ith row in the jth column, where I and j have to be appropriate indices. So I has to be between 1 and m, and j has to be between 1 and n. So that's what I'm saying just by writing this little thing down. It's a lot of information in compact space. And I'm going to do a similar approach for another matrix, B. So I'm going to use J for the index for the rows, and I'm going to use K for the index for the columns. And now for the dimensions of B, I'm going to say N by R. So there's a lot of unknowns here. M is the number of rows in A. N is the number of columns of A, but it also happens to be the number of rows of B, and that's going to be crucial. That's the most important part of what I've written down, and that's going to need to be the case for matrix multiplication to be defined. Now, in the first matrix A, I'm using I for an index for the rows, and J as an index for the columns. Well, in B, I'm using J for the index for the rows and K for the index for the columns. And that you might ask yourself, well, why am I using J as a column index here and then using J as a row index over here? Well, it's because the bound, it works out so nicely because over here, J has to be between 1 and n, right? Because it's a column index and A has n columns. But over here, J is a row index and B has n rows. So again, it's got the exact same bounds. So that's part of the reason why I'm using J as an index in two different contexts here. So it's a column index for A and it's a row index for B. So we'll come back to that in a moment. But the important part of everything I wrote down is that the number of columns of A, which is n, and the number of rows of B, which is also n, those have to match up for this to make sense. But if they do match up, then here's how we'll define the matrix product. So the product, that's the name of it, just like in the case with real numbers, and we write it as in this fashion. Just write A and B right beside each other. So we're now going to define what that means. So, well, if it's a matrix, what are its dimensions? It turns out that its dimensions are going to be using this M and this R. So it is the M by R matrix defined by the following rule. And just like with the previous operations, the rule I'm going to give you is going to be a formula that tells you how to calculate one entry at a time for the product AB. So because it's an M by R matrix, I'm actually going to use the index I for rows and the index K for columns because K has to be between 1 and R, just like it did up here, right? K has to be between 1 and R, so the bounds work out really nicely. So it just makes sense to use those two indices for use these two letters for indices for rows and columns of the product matrix A and B. So what's the formula? Here's the formula, and it's a definition. So I'm going to use that full colon beside the equal sign. Here is what it is. You're going to take the sum of the products of these entries. I'm just going to take Aij. I'm copying those entries exactly. And then this entry here, Bjk, I'm even copying the indices. Okay, so you're going to multiply those. Now, what are I and what are K? Well, I and K are actually fixed in this case because they represent the row and the column whose entry you want to compute from the product. So I and K are already bound in that sense, but J is unbound. And that's actually works out perfectly because we're going to use this for the index, for the sum, right? We've got a summation notation that we've started but haven't finished. So the index for the summation is going to be J. It's going to start at 1, and it's going to go all the way up to n, right? Which is whatever this common value was here, the number of columns of the matrix A and the number of rows of the matrix B. So that is your definition of a particular entry of the product matrix AB. And that's going to be, this formula works for every I and K such that the bounds are appropriate, as always, right? So I has to be a suitable row, so it has to be between 1 and m. And the other requirement is that K has to be a suitable column index, so it has to be between 1 and R. So 1 has to be less than or equal to K, and K has to be less than or equal to R, and that is the definition of matrix multiplication. So we've got a summation notation that we have to unpack just to compute a single entry of the product. So it's quite computationally intense to compute a product of two matrices, especially if the matrices are large. But let's do an example where they're still fairly small and it's manageable to do this by hand. So let's start with a pair of matrices. I'm going to write down a matrix A, and it's going to be a 2 by 3 matrix. And I'm going to write down a matrix B, and it's going to be a 3 by 4 matrix. And here are the entries. All right, so first I want to do something called, and this is my own language, I've never heard anyone else call it this, but I like to call these dimension diagrams. And what I use them for is just to make it clear that a product either is or is not defined. This is the justification I'll use. So start by, we want to talk about the product AB if possible. So let's do the dimension diagram over here. So I'm going to write down the matrix A, and I'm going to write its dimensions right below. Right, it's 2 by 3. 2 rows, 3 columns. And the matrix B has 3 rows and 4 columns. And the first thing we note is that these two numbers match up. And they must. They must match for the product to make sense. So, and the fact that they do, that means the product does make sense. But there's more to it. Now we'll take these two outer numbers, the 2 and the 4, and we'll bring them down to get the dimensions of the product, right? This is like your M and your R, right? This is your M and your N and your R. Your M comes down here and your R comes down here, just like it says in the definition. So that's how you can get the dimensions of the product. So let's say this is the dimensions of the product AB. Okay, so that's what you can do before, just as a cautionary check, right before you start to do a matrix product, just to make sure it's actually defined. You can draw this little diagram. You're checking to see if those two entries agree, or these two numbers agree, and then you're also determining what the dimensions of the result are. So the result, AB, is actually going to be a 2 by 4 matrix. So I'll just leave room. So we got 1, 2, 3, 4 entries in the first row, 1, 2, 3, 4 entries in the second row. So, and to compute each of those entries, we're going to have to use this formula, which is a little bit of work, isn't it? Let's start with this entry up here. Let's compute the entry from AB, and I'll start it down here in the same color. It's in the first row and the second column. Well, let's use the definition, right? So you're using the definition up here with I equal to 1 and K equal to 2. So when you write down the I over here, you're going to put 1, and this K is going to be a 2. But the J is going to be left as a J because that's the index for your sum. And then the N up here, this N is going to be whatever this common value was here, the 3's, right? So that's going to be 3. So if we write this out carefully, we'll have the sum J equals 1 to 3 of A1J, pardon me, BJ2. I almost wrote a K there by accident, but that K has to be replaced with the 2 here. So that's what we get. So this is the sum that we have to evaluate to figure out what this entry is going to be. So let's unpack the sum, right? Start with your initial value of the index J as 1. So we're going to have, just rewrite the J's as 1s and leave everything else the same. So you have A11 times B12. So that's just, I'm writing this expression out where J is equal to 1. Now do it again, but increment J so it's one number higher, so J equals 2. So you're going to have A12 times B22. And then increment J again, you get J equals 3. You're going to have A13 B32. And that's what you get if you write this expression out with J equals 3. And now I stop, right? Because I've hit J equals 3. That's the final value for the index. So this is the sum being expanded. And before we now grab what these, well, actually, this is exactly what we're going to do. Look at what these entries are, because they all come from the entries of the matrix A and the matrix B. Now start with A11, A12, and A13. That's A11, A12, and A13. Those are the entries in the first row of A. I'm going to write a 1 there just as a reminder. Now, B12, B22, and B32, those are actually the entries of the second column of B. Right, here's B12, B22, second row, second column. B32, third row, second column. So that B12, B22, and B32, that's this column here, the second column. And you'll notice that the 1 and the 2 here in the subscripts to reference the entry AB that we're trying to calculate, that 1 corresponds to the first row here, and that 2 corresponds to the second column. So that's what you're doing here. You're just taking this number, multiplying it by that number, taking this number, multiplying it by that number, and taking this number, multiplying it by that number. That's exactly what this formula tells you to do. And then you add up the products. So what will we get if we do that? We're just going to get 1 times 1 plus 2 times -1 plus 4 times 7. And you work that out, you're going to get 1 minus 2 plus 28. That's going to be 28 minus 1. So you end up with 27. Okay, finally, we've got ourselves one entry calculated, 27. Okay, so let's do one more entry. How about we compute the entry down here, the entry that's in the second row of AB and the fourth column of AB. And I'll do that one in the same color down here so it matches up. So we want the 2, 4 entry of the product AB. So what are we going to do? We could do this again. We could follow this rule, use the summation, but let's just make this observation. Right over here, we wanted the 1, 2 entry. We took the first row and the second column. If we want the 2, 4 entry, take the second row and the fourth column of B. Right? So we're going to go 2 times 3, 6 times 1, and 0 times 2, and add up those products. So, I mean, if we followed this style, if we followed the formula carefully, we would get the exact same thing. But this is just a bit of a shortcut. So 2 times 3 plus 6 times 1 plus 0 times 2. And if you work out all those products, you're going to get 6 plus 6 plus 0, which works out to 12. Okay, so that gives you this entry as a 12. So to compute each individual entry of the product matrix AB, you have to do 3 products and 2 additions. Right? So there's quite a bit of arithmetic just to compute a single entry. And that's one of the things that stands out as different about multiplication from the other operations. But that's matrix multiplication. I'll leave it to you as an exercise to fill in the rest of the entries. I'll write them down now that you can use as a check, but I encourage you to, before you go on to the next video even, just use the process I showed you down here to fill in what each of these other 6 entries are going to be. But at this moment now, I'm just going to write them down so you have them to check your work. So you're going to get a 12, 8, -4, 26, 30, and then 13. So, and like I said, for each one of those entries, there's some work to do. You have to do 3 products and 2 additions to get your result. So I'll leave it to you to check those in detail. But that's matrix multiplication.